Welcome to video 3 on Euler's form of a complex number. For this video you need to know what the modulus argument form is and what the Maclaurin's expansion for e to the x, cos x and sine of x is. You also need to be familiar with your powers of I. Okay, let's begin with a complex number z, which is equal to the magnitude of z times, all in brackets, cos theta plus I sine theta. Now I'm going to write down what the Maclaurin's expansion of cos theta, sine theta and e to the theta is, which is just the same as if theta was an x. Now I'm going to replace cos theta and sine theta in z with their Maclaurin's expansions, giving us this very ugly equation. I'm now going to expand the I times sine theta bracket and reorder everything in ascending powers of theta like shown. I'm now going to do a quick recap of what the powers of I are. So we know I to the 0 equals 1, I to the 1 equals the square root of minus 1, because that's its definition. We also know I squared equals minus 1, I cubed equals minus the square root of minus 1, and finally we know it is cyclical and comes back to the I to the 4 equals 1. Knowing this, we can now rewrite the expression as modulus of z times by, in brackets, I to the 0, because we know that 1 is equal to I to 0, plus I times theta, because that's what we had in our last expression. Now the next two terms are negative, so we can replace the negative with an I squared. So we get I squared times theta squared over 2 factorial plus I cubed times theta cubed over 3 factorial. You've probably spotted the pattern and realised the next two terms can be written as I to the 4 times theta to the 4 divided by 4 factorial plus I to the 5 times theta to the 5 divided by 5 factorial. Now I could go on forever until I reach the 2n plus 1 term as I shown in the bracket, but instead I'm going to define a new variable, a, which is equal to 2n plus 1, and put that as my formula for the last term. Now it may look familiar already, but in case it doesn't, I will now factorise the powers in each sum. Now it must look similar to the e to the theta expansion, except theta is replaced by I theta. With this being said, we can replace this whole expression to leave us with the magnitude of z times e to the I theta. This form is very nice and is known as Euler's form because of the e. Thanks for watching, and in the next video I will use this to prove de Moivre's theorem.